Okay, we're looking here at section 7.1. We're estimating the population mean mu when sigma is known. And as was pointed out in a video we watched in class, that is rarely the case that sigma is known. So the more realistic stuff you would conceivably be doing is starting in section 7.2. So anyway, in this chapter, we begin looking at estimation of a population parameter, or of population parameters in general, using sample statistics. How do we estimate the population mean, for example, in this section, using the sample mean as a point estimate? So in 7.1, again, we assume sigma is known. We take a simple random sample of size n. And then here's some information that you saw back in chapter 6. If you know that your X distribution is normal, your population is normally distributed, then any sample size will do. That should sound familiar. That's theorem 6.1. If X is not distributed normally, or we don't know its distribution, we have to have a sample size greater than or equal to 30 so that the central limit theorem applies. So what we're doing here, we're going to use X bar as a point estimate for mu. We have this margin of error that we look at, the absolute value of X bar minus mu. We don't know exactly what the error is since we're taking a sample and we don't know mu, right? So the idea is what we do is build a confidence interval around our estimate. X bar plus and minus some amount of error is what it turns out. So for example, we might want our confidence interval, we might want a 90% confidence interval. In other words, we might want to be 90% confident that mu is in our interval. Usually the levels that you run across are 90, 95, or 99%. Although the table in your book has more than just those, and we're going to take a look at that in a little bit. So we need to be able to find, if you're doing this by hand, a critical value Z sub C for our given confidence level. Make sure you look over page 336. And then we're going to use table B in your appendix section from areas of a standard normal distribution. A little bit of background developing what we want to do. You're not going to be tested on can you develop this formula or anything like that, but I want you to just see how the reasoning behind it. We want the probability that Z is between negative Z sub C, some Z value for our level of confidence, and less than the positive of that Z sub C. We want that probability to equal C. And you can see this on page 361, how this formula is developed. Back in chapter 6, we standardized X bar values. X bar from a sample mean, right? We saw that for a sample mean, to convert X bar to a Z value, it's X bar minus mu divided by sigma over the square root of n, not just sigma, right? And if you multiply this inequality through this part right here, you get this. So we're putting multiply through by the denominator, I should say, on all three parts of this inequality. It gives you this. The probability that negative Z sub C times sigma over the square root of n is less than X bar minus mu is less than Z sub C times the square, sigma over the square root of n. And that probability is equal to C, our confidence level. That means that this Z sub C times sigma over the square root of n quantity, that is our error, E. It is the maximum margin of error, the maximum of how much X bar is going to differ from mu for a certain level of confidence, C%, whatever that is. And I wrote right through it and I don't know what. There we go. All right, so when you substitute X bar minus E, or excuse me, when you substitute E into this start equation right here, you get this. This is the result of what we want. We are actually calculating the probability that mu is between x bar minus some amount of error and less than, or between x bar minus an amount of error and x bar plus an amount. So greater than x bar minus e, and then mu is less than x bar plus e, and we are C% confident, whatever C is, that that's the case, okay? So let's take a look at how to actually calculate that using a table. Oh, also, before I do that, make sure you look over example 2 on page 365, and then read over interpreting confidence intervals on pages 365 and 66. All right, so I'm going to share specifically the table here. And what we're going to do, let's see where the, yeah. So here's your table 4A, right? Your shaded, your positive Z value, and it's shaded off to the left of it. And we've already looked at how to calculate areas under that table, which is all of the inside of the table, right? You go down to the appropriate Z value down here to the 10th place, across the top to the 100th place, and find the area under the curve, shaded as it is above. What we want is down here at table 4, B, confidence interval critical value Z sub C. And you can see the level of confidence is given here in the first column. Notice here they have other levels than what I mentioned. So they have, for example, 75% and 80% and so on. Well, the reasoning behind this, what we're doing, here's my Z distribution. Let's say, for example, we want to find we want C to equal 0.90 or 90%. That's right here. Well, that corresponding critical value is 1.645. And so what that means is, if you go up here to positive 1.645, and back here to negative 1.645, the area between those two values, so like this shaded region right here, will be your Z value for a 90% level of confidence. So this will be 90% of your curve, that shaded region. All right. And I think I misspoke there. Your Z value for that level of confidence is the 1.645 that we got from the table. 1.6 at the back, 645. All right. So let's look at an actual example using the table. And then I'm going to show you how to do it on a graphing calculator. All right, so I wrote, we're going to take a look at a problem up here. Page 371, problem number 18. It concerns watermelon crops. So it says, what price do farmers get for their watermelon crops? In the third week of July, a random sample of 40 farming regions, so you can see N equals 40, gave a sample mean of X bar is $6.88 per 100 pounds of watermelon. Assume that sigma is known to be $1.92, $1.92 per 100 pounds. And again, sigma is rarely known. So they're saying assume that that's sigma, right? We're just going to take a look at part A. Find a 90% confidence interval for the population mean price that farmers in this region get for their watermelon crop. And then what is the margin of error? Well, we need to calculate the margin of error anyway in order to find X bar plus and minus the amount of error, right? So first we need the Z value, which we already just looked at a few minutes ago. So the Z value for a 90% confidence level, we go down here to the table and we look over here and it's 1.645. So our error is going to be that Z value times sigma over the square root of n, which is the square root of 40. And we're doing dollars and cents here, so I'm going to round this to the hundredths place. I'm doing this on a calculator, just a handheld calculator here. 1.645 parentheses 1.92 divided by the square root of 40. And that is approximately 50 cents, rounded to the hundredths place. I'll write that as $0.50, okay? And now what we need to do to calculate our interval is find X bar plus the amount of error and minus the amount of error. So that's going to be X bar is 6.88. We're going to add and subtract from that 0.5. I'm just going to write it as 0.5. And let's see what that equals. And round that to the nearest hundredth place. And so what we're going to get is $6.38 up to $7.38. All right. So then how do we interpret that? Well, generally, you'll see this as you read through examples and check your odds in the back of the book. Generally, it's worded something like, based on this sample, we can be 90% confident that the mean price of watermelon per 100 pounds is between $6.38 to $7.38, something along those